everyone. Welcome to another meeting of our reading group. It is the last meeting of our reading group for the summer. We will return back in September and we have an exciting list of speakers, so stay tuned. We will release the speaker list soon. Today, we have another great speaker, Dinesh Manocha from Department of Computer Science from Maryland University. As always, if you have any questions, feel free to raise your hand or drop the question in the chat. Without any further ado, the stage is all yours.
Thank you very much, Puna, and good morning to everybody from Maryland. It's a really honor to give an opportunity to speak to you. Some of the work my group has been doing on what we have broader topic. Audio processing is a very old topic, studied in different fields, signal processing to virtual reality to AI. And we're looking into, in the era of large language model, generative AI and agentic AI, what does it mean? So this is an overview of a lot of work we have done in my group with collaboration. I have a web page here. This web page has a lot of details of our papers as well as a lot of latest videos. So you can look at more details of that. Before I really get into my details, let me acknowledge all my collaborators. It's mostly my students. Some of them are still PhD students at UMD and some of them graduated. And among all the students, I really want to point out Shreyan Ghosh, who is a senior graduate student NVIDIA fellow, who has been leading many of these projects. And we're also fortunate to work with a lot of industry partners. You'll see some of the work represented with Adobe and now with Dolby Labs and also with NVIDIA. So we really appreciate all the great collaboration and support we have from all the industry partners. So, audio is a very old modality. This is not a new idea. It's been around for a long time. And it's getting more and more important because if you look at even the latest release from Google last month, Gemini 2.5, they were showing generative AI and they're saying not only you can make high resolution movies, but you can make movies which are not silent. So they already have like 8-second movies with audio. So audio is really getting really a lot of excitement in the generative AI world right now. But before we do into that, humans and of course animals in our daily life, audio is a very important sense along with vision. We have a lot of perception, audio, visual, along with tactile comes up. And it's well known that audio cues enhance situational awareness communication for us, right? And when we talk about audio, you'll see me speaking that top point multiple times in the thing. So we'll classify them into two kinds of audio. One is verbal audio. So speech, right? If you can hear me speak and you can understand what I'm saying, it's a verbal audio. So here's an example of verbal audio, just simple speech.
In his hand, he had that acting degree. He had a dream and he wanted to fulfill. He was in this dreamland.
So this is just a simple spoken speech, and speech has been well studied, and especially in the last 13 years after deep learning took off in early 2010s, speech was one of the applications which got a big boost from deep learning and machine learning. But actually, for a lot of my talk, I'm going to focus on what we call non-verbal audio, and these are things like sounds like I'm sneezing, coughing. You can hear some background noise, traffic, thunders. So literally a lot of our work has been focused on non-verbal audio because there is a lot of work on speech, especially a lot of commercial support. So here's an example of non-verbal audio. So this is like a typical environment sound, right? We hear all the time, a background noise, a door closing, somebody banging the door, coughing, right? And as I said, and especially towards the very end, a little bit talk also about music. Music, another wonderful, we all love music and spend a lot of money on that. So what can we do to do audio processing on non-verbal audio? So that's going to be a big focus of this talk. So as I said, especially in this era of all kind of AI technologies, we're talking about agents. So it's pretty well known that audio is also essential for creating intelligence AI agents, because we want agents to do all kinds of jobs. And I'll come towards the end on robotics, robots operating in your physical world, doing it. Even we see like, Waymo cars coming at many places, or Tesla robot taxis, and they hear a sound like a siren. So they should be able to react to the environmental sound comes up there. So clearly reasoning and understanding about the audio of the environment is very important for all AI agents, Now, of course, if you look at something like this, even when you're, for example, cooking something, right? And this like show you a video here that sometimes, human relies, of course, a sense of touch for humans, but robot don't have a good sense of touch. So how does a robot know the spatula has touched the pan while it's like flipping the bagel? And sometimes, you hit the spatula with the pan, you hear that sound that comes up there. And they can hear and speak just like humans can. So, we're getting into era of smart chat box, making all kind of sound, just like human-like experiences, and that's why we're going for it. So not only that, but a lot of things like, nowadays happening in students nowadays, I feel that I ask people to read a paper. I say, good luck. They will just go to like latest generative AI system and do a, audio, like summarize the paper and do it. Pretty soon I'll say, okay, you know what? Who wants to hear a 1 hour talk on Zoom? It's just a too long a lecture. Summarize the talk, right? So we're getting stage, especially Gemini 2.5, summarize the movie, summarize the long sequence. And in the summarization, audio is a very important cue of the whole context of what's going on there. And if you just do movie summarization, if you only look on video frames, you will never get a sense because how the audio changes, how the background noise, the music changes. That's a very big intent on comes up there. And also, it's well known that audio can improve the content generation. So if you look at some of the earliest generative AI system from OpenAI and even to Google, were doing like movie generation, text to movie or text to image. So here's one of the examples of like text to movies. You can see this, some playing around. Now, this was just what I call a silent movie. And one of the basic things that Google is promoting with Gemini 2.5 is no, they cannot make no longer silent movies, but movie with audio. So if you have the same experience movie with some audio, see how it feels to you. So in movie and games, audio is a very, very important cue for anybody to understand, understand the content delivery. So this is, we want same kind of AI generated audio to be good of it. Now, there are a lot of AI systems doing audio perception. This concept is not new. This concept is on for many decades, So especially scene understanding can improve incredible audio thing, like, computer vision is about visual scene understanding, but physical world is audio visual. There's a lot of, if you go to any AI conference right now, from computer visions, ICCV, CVPR to the leading NeurIPS or ICML or ICLAIR, or even some NLP conference, you'll see a lot of work on doing audio visual. That's a very hot topic. My group is actually doing a lot of work and publishing a lot of papers on that. So audio is there. And I'll talk about especially egocentric perception, which is getting really popular with smart glasses coming up there. Scene captioning, you can something like this audio visual scene captioning that if I just say, if there's a caption without audio, this is something like this, a dog, black dog sitting on the sofa. But if I say caption with audio, it's much better. You get a much better understanding. And of course, GPT-4o, which I think came around in around late spring or early summer 2024, was probably one of the first generative AI system with the integrated hearing and speak capabilities, and that has really taken off. There's a lot of big companies that are doing amazing work on that. So here's the example of, this is for a year-old video, how GPT-4 can hear and speak, and you can see how wonderful a job it does. So let me play this example for you.
Hey, how's it going?
Hey, Rocky. I'm doing great. How about you?
I'm awesome. Listen, I got some huge news.
Oh, do tell. I'm all ears.
Well, in a few minutes, I'm going to be interviewing at OpenAI. Have you heard of them?
OpenAI? Huh? Sounds vaguely familiar. Kidding, of course. That's incredible, Rocky. What kind of interview?
Well, it's for a software engineering role, but
So you can see, you can have a natural conversation with the chat box. In fact, there's other, very nice company called sesame.com, SESAME. And when you actually go and try out their demos, not only they talk to you, but it sounds very natural, the naturalness of, what I call human-like experience. So these systems are getting so good that, your conversation with them, because the audio background is so good with the speech. So Sesame has done some really amazing job, and go and check it out if I play with the demos there. So this thing, this is again examples of audio thing. Now there's also work like in computer vision, we're saying that if you're given a scene with audio and video, it improves the scene perception, what room you are in, what's a room size. So if any computer vision system has audio cues, it can do much better scene understanding. And you see lots and lots of paper in computer vision community on this thing. Here's an example I'll tell you. the robot navigation and room scene. You'll see a robot, on the right-hand side is a piano playing with like a layout 2D map. On the left-hand side, robot walking. And you'll see when the audio cues robot hears, you can isolate where the piano is located. Your scene understanding become much better. So humans use this, this audio localization and spatial audio to know direction of sound. So just like, how you do your daily tasks, your audio localization or audio understanding and spatialization is very important part. So these are all the things. As I said, these problems are not new, and especially what I'll talk about, mostly audio understanding and audio generation, which are two aspects of audio LLM. And especially this field of, audio understanding, there have been a lot of good interest. I'm just giving a short sample of papers. You feed them, a lot of initial encoders at audio spectrogram transformers. And, initially modeled by CLIP, they came up with a CLAP, which is audio language model. This was some earlier paper in 22. This is some of the work, our work on Compay that came up there. And then some recent work is, audio LLMs using LTUs, which has come up. So this is literally, now in the last 4 or 5 years, this has really taken off, audio understanding, and it's becoming a very hot topic, just like, visual understanding or something like that. And then there's a whole thing of audio generation. There are pretty good websites on, from sonu.com and Meta has it. Gemini has done some amazing work where you can generate music and different kind of sounds, text to sounds there. So here's some example of, we tell like a diffusion model of audio gen, this 122, recreate a gentle rainfall with thunder. So instead of, recording it, you can now generate with generative AI like this. Let me play this one. You can see we have a capability of generating simple sounds, and this is just getting better. Here's an example of, audio storytelling, wave journey. So this is an example of how you can make pretty good generation of a story. I play this video here. This is on 2023.
Good evening, ladies and gentlemen. This is the BBC World Service, broadcasting live from the heart of Paris, the City of Lights, art, and it seems ever-deepening mysteries. The date is the 15th of June, 1926, and we have a rather unsettling...
So this is, I won't play the whole thing, but you get a sense of, where things are coming up. Now, what are the challenges? Why I would say there's a lot of initial work. Of course, the whole initial success of generative AI, OpenAI, ChatGPT was text. The field of NLP has seen major changes. It's probably one of the biggest use case. Then we saw like, all the things like with text to image, text to videos, that's getting better. Audio, I would say, is much less done work than text or video. So that's why most use of generative AI comes up there. And one of the challenge problem is, all this generative AI machine learning is on data. Like the reason ChatGPT works well because they're trained on internet scale data, and somebody estimated they're like documents with 1 trillion words, right? And even for videos, I've heard YouTube has 20 billion videos. So that really comes up. Some of them come with audio. But if you look at, for example, as I said, this is all about tokenization. For language, you got billions of tokens. For vision data sets, these numbers are probably outdated. Again, we're talking many billions. Now, speech, which is pretty well studied for speech understanding, at least the speech community is, especially some big language like English and maybe Chinese, you got about larger data set about 60,000. So compared to billions of tokens for language and vision, speech go to 60 plus. We talk about tens of thousands. And especially our focus on non-speech audio, then the life gets much harder. So till we last counted, and with basically a few less than 1K hours. Now it's getting better now, but look at the order of magnitude, 1K versus 60K versus billion. So one challenge has been limiting audio data sets. So that's been one of our big focus in the last 2-3 years. If you want to push a state of the art, we have to develop and generate new data sets. That's just like the way it is. Second thing is reason-centric metric, right? So complex reasoning, distilling large models for reasoning still remains a challenge. That's still reasoning is a very hot topic right now in the OpenAI community. So,
got you a present.
I'm tired and I want to go to bed.
You heard this audio, and if I ask a question, what are the audio acoustic events in the given audio? Most of humans can easily, in fact, human has a very good sense of repurposing audio stuff, right? And we ask this question, complex instruction, and how do you reason around it. And some of the initial work was only a few seconds audio. We have actually pushed some of our recent work moving to 5 or 10 minutes, but we still, cannot do a long audio sequence. Like if you give me a movie, of course, if you do audio speech to text, if it's speech, but if I play a long movie with background noise or, sounds of music mix, something 20, 30 minutes, we can't handle it. So this is where things are really challenging. And if you look at the audio encoders, in the audio domain, best encoders get 50% audio set, whereas computer vision, thanks to image database, 95%. So I would say in many ways, the amount of effort, data sets, processing methods in audio really lack. So which on the other hand, look at this way, especially for your PhD students, there's a lot of room for improvement here, right? This is where this is well studied. So how we can do things like this. So this is exactly what big challenges we are trying to address here. Here's some example of, state-of-the-art audio model. So especially in real world, environmental sounds are much more compositionally complex. So what does it mean? You hear all kind of noise. If you walk on the street, you hear something like a dog barking on the following by a person speaking, like this audio. This was generated by stable audio. So if you're given a complex slide is like compose, you see dog barking and a human speaking, which I didn't really play all the time. It comes up there. So you need better audio data sets, better training, better model representation. And then, current state of the art model really struggle to complex audio. So this is where challenge comes up. You imagine basic music, speech, dog barking, environmental sound, you mix them together, and current system will So this is again, right, what sounds could be coming up, and most system will fail on sounds like this and long video. So this is a very long audio. So suddenly, you'll hear this.
Hello? Anyone here? Sorry.
So again, in interest of time, I won't play it, but hopefully you can, there's some of the video out there saying, if you give a long audio and hear for a minute or two and you ask, where was the element of fear? Humans can do very well, animals can do very well. Of course, animals can't communicate, but this is where things are okay there. So we need long encoding and come up. So these are really all the problem we are dealing with comes up here. So as I said, the large language models, the fundamental idea is that basically large audio language model, we call ALLM or LALLM. We have seen both kind of term being used or just ALM. So the grand goal is to basically understand, generate, interact with audio, just like we do with language, right? So again, a biggest challenge being that, there was this thing. Now, before LLM became popular a few years ago, right? So there was CLAB inspired by CLIP, the pre-key, pre-LLM, which comes up there. It was used for classification, text, audio text retrieval, text audio retrieval. And now, with LLM taking off, right? Especially text and then video audio, clearly there have been a lot of work. And this is only a small sample of, Gamma, some of the work we have done at LTU, Quen, Solomon, which are capable of captioning, reasoning, and open-ended question answering. So this field has really taken up here. Here's an example of few of the same things. So this is not the LLM. We are not the first one. There's a whole debate about open source, open weight, or proprietary or closed. So that's not the topic here. But you see some of them here, open source. Some of them, Gamma is done by us. Audio Flamingo 2 and Flamingo 3, I'll talk about, done by us. But some of the best ones, especially Gemini 2.5, I've been playing with it. It's quite impressive. But I mentioned about Sesame, right? Sesame is one of the most natural sounding audio experience. And I would just say, go and try out their demos. It's really, really amazing. You'll see what they're doing. And then they're open access. So these are clearly all three fronts. We're seeing a lot of advancement happening, and I'm sure there are many more which I've skipped out here. So let me start with some of the work we have done to tell you where we are today and how do we want to do it. So one of the first, when we started working on this about more than 2 years ago, we say first challenge for non-speech audio was, getting complex benchmark, and especially complex with compositional reasoning. We addressed the gap. So first we proposed something we call like a whole framework and a benchmark for compositional reasoning. I explained to you a little bit earlier. We call it CompA. It was presented at iClear about a year ago. The idea was, understand relation with text in caption and corresponding on the audio. So how do we basically this compositional reasoning? And literally, when we started this work, this is way back in about 2 years ago, we found that current benchmarks are not really good enough. We found that, if at that time, this is from 2003 and early 2004, that we look at the benchmark, we found they really did very badly job in compositional reasoning, and those LM did not this thing. So this was saying, so to really overcome this thing, we first proposed a benchmark, call it CompA, and it has two parts to it, which I won't go into details. CompA order, which is to evaluate ALM capability for occurrence of multiple acoustic events, and what we call CompA attribute, which understand attribute binding for literally multiple acoustic events. So because the whole idea was we can do more things, multiple events and like that come up there. So here's the example of composition audio that a tiger growls followed by people talking. This is the kind of sample provided again, and this is just example of your reverser thing. People talking about tiger growling, so you can all kind of composition characteristics. These are, what I said, different kind of sounds, different audios put together, come up here well. Here's the example of a child sneezing, adult laughs, So similar kind of thing. I will not play too many audio samples because I don't have time. And some of these are on the website. You can go and try them out. But this was the first benchmark, which was really pushing the state of the art towards this composition audio there. So we literally present new methods and also to how to evaluate them. Again, we come with a formulation of the text score and audio score and the combined score. So the idea was you have different combination, the audio score, how you model that. And this is a way of metric for doing compositionality. And at least when we tried the current state of the art on the current benchmark, all methods around, this is late 2023, did a pretty bad job. So we realized that there was a lot of gap here, our benchmark is there. So this was the first version of benchmark, which we released in late 2023.
Sorry, maybe before go to the result, there's one question that might be
Please go
relevant.
ahead.
Could you please explain compositional reasoning? Is it like audio question answering or not?
Yeah. So that's correct. You can think about is audio understanding, and as I said, so the bigger picture is that, as I said here, you're given a text and caption and corresponding content. So you can one idea would be exactly, I play this complex audio like a dog barking and human speaking. I give you this thing, I can ask you a question, hey, what did you hear? Or I can ask you a question, oh, did the human speak before the dog barking or not? So it could be any high level understanding, but a lot of examples are definitely question answering.
So it is not like asking the model what kind of reasoning do you make. You basically ask a question like what you hear, why you think something happens or something like that. It's a question answer things in this scenario.
Well, that's one thing, but I could just tell you, I just play audio to you and I can ask a question. So the question could be, okay, just tell me, what did you hear? What kind of audio? Let's take a simple, like imagine you're doing a hearing test, right? And you go to a doctor and you put a headphone and I say, hey, what did you hear? Or did you hear something like, but question answering is definitely the most common form of that. That's correct.
Nice. Okay, perfect. Thank you.
But it's just like, okay, think of you understand audio. You see, like if I tell you, you heard the audio, write out what you see. So exactly, but question answering is a good platform for that. Yeah, and please feel free to ask any question, where things are there. That's good there. So that's coming up there. So this was exactly the first benchmark. And, we also did a lot of CompA Lab negative training. I'm a little bit going over quickly because a lot of stuff to cover. And, I just want to give a level idea, especially this work is now 1.5 or 2 years old. So I don't want to spend too much time. I want to spend the latest work on Audio Flamingo 3. But literally, other thing was to make it, contrastive learning. We also introduced what is called synthetic data generation strategy. I'll talk about more Synthio method here. But one challenge was, how do we literally, we want to generate composition audio caption pairs, so audio along with caption. And as I said, the big focus was taking multiple single acoustic events and aligning them with audio pause and negative outcome. So this is a lot of effort went up towards CompA to make things happen, and the details are there. So we literally, did the benchmark analysis, compared composition A with that time thing and showed, that, on retrieval benchmarks, especially audio claps and Clotho, CompA and CompA clap literally, gave us much better challenges and results on how do we deal with them. So the first really benchmark to show that how we can, do analysis in terms of composition audios there. And this is on the zero shot audio classification benchmark. You see how the results are doing with our new methods, on this kind of methods here. So once we had the thing, this is the first work we started. This certainly started in 2023 late and early 2024. This was presented at EMNLP last November as an oral paper. Literally was the first general purpose audio language model we built, which has advanced audio complex reasoning and understanding. And as I said, Compe was a benchmark with some model, but this was the complex. So here's the audio sample you can hear. So this is, at that time in late 2023 and early 2024, we found the audio language model really struggled to do complex. This is exactly the question answering. You hear audio and question answering as just recently we talked about a few minutes ago, come up there. And how do we evaluate them, right? So literally, we literally compared, with the LTU, which was the state-of-the-art method when we built on Gamma, about an audio, how it does question answering, and that comes up here. So most audio, at least LLM, were using single audio encoder with a linear layer, and we had to literally improve on these aspects. So again, I will not go into details of that, my apologies, but just give a high-level architecture to really deal with it, there are 3 parts to it. There's a whole multi-layer aggregator with cross-attention and self-attention. We have the audio co-former, which is a big part, and then finally there's the MLP-based, soft prompt. So these are the big architectures, and I recommend if you're interested, go read the paper, why we made these choices, and I'm sure there are ways to improve upon it, but that was a decision we made that time to deal with it there. And also the training aspect is very important. You'll see as we go better and better audio language model, the training gets more and more complex. I'll talk about that towards the end, especially talk about latest Audio Flamingo 3. There are 5 stages of training. So this is in 2023, early 2024. We're doing Gamma was trained in what we call pre-trained on large-scale dataset audio language pair, and then it's trained on CompAR, which was literally the benchmark we introduced, literally to design framework. So we literally utilize them quite effectively to do a 2-stage training. And this was Gamma result. This is in, as I said, late 2023, 2024. We compared with state-of-the-art model that time, LTU, Solomon, Pengy, they were coming up. And we showed that, our Gamma gave better results. And this on the bottom, we also showed, 3 component ears that we have. We started ablation to show that if you drop that, how it hurts. So all the 3 components in the architecture are very important. So overall results are here, but you can also see lots of, ablation to show how it outperformed and how all 3 components had to come together to get good results. That was also very important there. The other challenge was, as I said, our goal was to do audio reasoning, as we just said, doing question answering there on complex audios. So we look at some of these benchmark, and you can see, again, we are seeing much better comparison over the baseline. This is around in early 2024 spring timeframe, how things were there. So literally, give you some example here. So this is an example of, here. So I'll play an audio. Let's see this here. So you heard the audio, hopefully, and now I ask the question. There's a question answering that based on the given audio, for the type of environment or the setting, and consider the duration of cars. So literally when we tried that time, this was the state-of-the-art of LTU, Solomon, and Pengy. We're getting all kind of, not the best results. And Gamma, at least the little environment is likely racetrack. So, we found it was doing much better. This is, quality results. Do that here. Here's the audio I'll play here.
All these are just little tricks to make you sound more like a voice. Trills.
So I asked a question, you heard the sound. Consider correlation of man's speech and music. What is a possible connection, right? Again, it's a complex audio. The human speaking, you hear like a guitar playing, something like that. And again, you'll see, the kind of answer LTU, Solomon, and Pengy did not do it. But at least Gamma made a much better, you can see the man is likely guitarist or instructors explain the process during a guitar. So again, this whole composition audio, we showed Gamma can do much better examples here. And so while we're doing this, there was Compe. So then we said, one way to push the more challenging work in this area is that let's make another benchmark, which is especially multitask audio understanding and reasoning. So a lot of our research in this area has going around it, coming with better benchmarks and better models, because we could not design model till we have good benchmark. So we presented MMAU, which was presented as Spotlight earlier this year in Eclair in Singapore. at least, is motivated by, I don't want to get into AGI, what AGI is, that's not the focus of this talk, but let's say you want to do something like 90% of skilled adults, whatever that means. So that's not really the focus here. But literally, the current audio benchmarks were really nowhere come close to it. So there's some audio benchmark people use for testing young children, but the current AI systems don't do it. So this was inspired. There were two works, especially in language, MMLU, and then in computer vision, MMMU. So those are very standard benchmarks, and any new, even if you look at Gemini 2.5, any new model come from OpenAI or Llama, they introduce it. So we were literally saying what they did for MMLU and MMMMU, let's equal for audio. So again, we follow the MMM, basically massive multitask, but we put an A for the audio part. So literally it's the audio equivalent of inspired by MMLU and MMIU. And again, you'll see, it's a very comprehensive audience and reasoning benchmark. We literally selected 10,000 curated audio clips with natural language question. Again, it's mostly audio pairs with language question, answers, spanning speech. But we also have a lot of environmental sounds and music. It's not just speech. Remember our focus on non-speech audio. That's the major focus here. So we literally, to make a good benchmark, this is just a breakdown. We have different 27 skills, some reasoning, some information extraction. Hopefully you can see the details, more details in the paper. But literally to show three kinds of things, we will focus on speech, which of course are well studied, music, and we call sound, everything which is non-speech and not nice music, like me coughing, door slamming, traffic noise, we just call them as sound. So we literally try to make sure all three are represented quite effectively, and focusing a lot on actually non-speech sound, because that was the least amount of data set that was available there. And literally when we release MMAU, right, so I'll show you, this is a very interesting time. This was in late 2024. We evaluated all these models, state-of-the-art models there. And that time, in fact, the version of Gemini was version 1.5, right? And you can see there were literally scores were in 56%. It was still very low. We just tried to show, and even to ChatGPT 4.0 and Llama 3, state of the art that time, they were not good. By the way, recently we evaluated Gemini 2.4. We saw a big jump. It's about 70s right now. So clearly Gemini 2.5 has come a long way. I salute the Google team for doing it. But still, that just tells you how challenging it was for all benchmarks to deal with this MMAU. And Gamma was our own benchmark not doing well. So this is like different skills, because there are reasoning tasks, temporal reasoning, harmony and cloud progression. Again, you'll see we're finding a hard gap. This is like with something green hard, they're performing quite poorly. So this was just to show a complex benchmark for understanding and reasoning. And literally, we have been seeing how the performance is improving. When we started in old benchmark from 23, performance was less than 10%. And in early 2025, 60%. And I think with the Gemini 2.5, it's getting close to 70%. So this is test scores are getting better, but we still have a long way to go. While there was MMAU, I should give you a precursor. We're releasing a new benchmark later this summer, MMAU Pro. So we want to push more complex reasoning, right? More and more complex. That's the whole challenge. But it's just real world is so complex. We want benchmarks to capture that. So this is a work in progress, and hopefully we release this in a couple of things. Now, one other thing comes up, as I said, capturing real world audio is non-trivial. Is a lot of challenge comes up there. So literally,
Sorry.
okay,
There's
question.
one question in the chat, that's related to the previous part. Could you please provide an example of a question in MMAU?
Right.
That's it.
Okay, so let me just wait for it. That's an excellent question. I will show some performance of MMLAU when it audio Flamingo 2, Flamingo 3. So I'll show some benchmarks in about 10 minutes, and those are based on MMAU. You'll see that example. So great question, but give me 10 minutes and I'll provide you an answer. But one challenge come up, data set is that where do you get especially a lot of, recordings, right? Real world audios. How do we put it together? So we also literally saying, okay, we have some small scale data set. And, one of the big thing has been, can we augment this real capture data with synthetic data set? That's a very common trend, right? A lot of domains use synthetic data right here. And again, we inspired by both in natural languages and vision, where literally synthetic data played a very big role. You can see synthetic data and computer vision playing a very big role, but we did not, we want to, again, the same thing for audio space synthetic data set. And literally, at least the previous noise augmentation method, which we use for audio, do not capture the diversity, especially with the complex audio that I've been talking about quite a bit. So this was something we proposed Cynthia, and this was also proposed in like literally late summer, fall 2024. The work was done and accepted and presented Eclair. Again, they said Eclair there. And this is an example of, how traditional methods literally did not do a good job, because as you generate the classification accuracy, and with Cynthia, in Brown will do it. And this is how we did some more work on that. So I'll just show you, I don't want to spend too much time. It's again a benchmark generation method. But literally, how do you take some real world scene? This is example of a sound of a bus, and how do we deal with it? I'll play the audio here. So this is like a small real world scene, bus comes up there, how buses sound in different regions, and crowds come up there. And literally we take this bus and, we basically take it from a text to audio model and train an audio. This is how we take a lot of samples and doing that. So again, I'll skip this part because this is another benchmark and synthetic data benchmark there, but how to get realistic synthetic data sets? I'll skip that because I want to talk Audio Flamingo 2 and answer the question about complex audio understanding. So this we also did a lot of work on text to audio model with preference optimization, because the big challenge, with synthetic data is, you reduce the sim to real gap, so that you want to make it close to real world audio and do things with it quite well. So this was about generic synthetic augmentations. Again, just a high level architecture. More interest, please read the paper and how do we do it here. So this is an example of showing, that if we literally generate data sets, how the performance gets up. So we're trying to show the synthetic method really give good answer, and huge performance gains come up here in this context right here. So that leads to the work I really talk about, the two lead audio models. We have worked quite a bit since summer of 2024 and ongoing. So this is joint work with the NVIDIA team. One is Audio Flamingo 2, and the third one is Audio Flamingo 3. I see a question again about real world audio here, right? So you're right, real world audio is literally, captured using some nice microphones in a real world setting. Let's say going to like a road, highway traffic noise or dog barking. So real world audio is indeed real world recording. So that's the ground truth we do. But since recording is very expensive to big data sets, we want to generate complex synthetic. So that's what we want to do basically like that. And of course, you can apply all kind of filters applied to them. But yeah, those are standard, audio processing or signal processing methods. We can do that. Okay. Hopefully I give you some fair on that. But let me come back to the two things I really want to talk about, Audio Flamingo 2 and Audio Flamingo 3. So this is joint work with NVIDIA. We've been working quite a bit on them. So Audio Flamingo 2 came up last February. Actually, it's going to present at ICML, which is going to happen mid-July in Vancouver. But literally this shows, that we showed these are different kind of benchmarks there. The previous state of the art of the different model was shown in this purple line. And literally you can see with Audio Flamingo, we literally pushed the accuracy quite far. This is when we released, this came out in February earlier this year. So it was state-of-the-art LLM that focused on two main aspects. Again, audio understanding and reasoning. So we developed an FM clap to generate that. But using Cynthia to generate what I call synthetic data at scale, because data was a critical part. We didn't have a lot of real-world data. And secondly, before Audio Flamingo 2, most audio language models were doing very small audio, like 5 to 10 seconds. So we want to do long audio understanding. It's not, you play long one, and we really pushed that towards something like, with about 30 seconds to 5 minutes. So that's what we did things there. So we also did another benchmark called long audio, because there were not too many long audio benchmarks from it there. I do see a few questions, but I think let me just hold off. I'll probably answer them, and you see some samples here, and some of the question will be answered by the example I show. And of course, as I said, the training part. So one of the things we are also doing if you look at all the audio models, the three parts, we need more complex benchmarks, long audio, augmented with synthetic. We're doing more architecture changes. But in each of these models, the training was more complex. So training was a big part. In Gamma, there was 2 stages, and you'll see now we're doing 5 stages and more complex training. So here's just an audio overall architecture. You take some audio like a female where the boy is barking, have a sliding window, perform AF clap, which is our version of clap, Audio Flamingo AF, perform transformation layers, and then generate these different gated versions and get LM blocks. So this was literally, and then tokenization. So this is like a basic architecture of audio LLM. We built on previous ideas and extended that. And then literally, you're given some complex audio with female voice and dog barking. The combination of barking is unusual and unexpected. So this is where, we'll do the reasoning about what's going on here. And as I said, the training itself was quite complex, multi-stages. We have pre-training, fine-tuning, and long fine-tuning, just as typical for all LLMs. We did the same thing right here. So one is goal idea was, AF clap. We literally generated on what you call 8 million audio caption pairs. We needed much more data. We generated from long videos. This was generated by previous work by Venkataramanan in long and short videos. We looked at those ideas from MLLM, which was, as I said, well-known benchmark in the language, and another one is this space. We've generated audio caption data with that. And for training, we also did different things like linguistic invariance, compositional reasoning, as well as other components. So this is example of, I'll just show it, and hopefully I show some example which will answer the question I'm seeing. So these are all the details about how do we do the representation and training, which was a big aspect of Audio Flamingo 2 and going around there. So this is what we call on the benchmark. This is audio skills, large scale synthetic reasoning. So this is exactly question answering A for 4 million pairs. And literally, the question answering part comes up here. So these are different kind of AQA data sets, temporal reasoning relationship, and general reasoning. Again, my apologies for really covering a lot of material in a very short duration, but I just want to give you our idea, and hopefully that you can go and read the paper on the website, which has all the details about all aspects. Like there were literally a lot of components we took into account: contextual speech reasoning and contextual sound event reasoning. So speech sound as well as sound reasoning, and how do we deal with them? So this is a data set, one of the first data sets for long audio. Literally when we released this is last spring, it is about 262,000 and unique audio question answering, and about 80,000 unique video audio. So this is like the first one pushing it. And if people want to work with us, please contribute to us, because I think this should be bigger community efforts, where we can work together. Different categories of audio sequences, different kind of questions answering, temporal, plot, complex, and different duration, just to show that we are generating a lot of diverse data set. So let me show some results to you, and this hopefully will answer question, or some of these are based on MMAU, and hopefully this will also convey to you a sense of what is complex reasoning right here. So of course we do the benchmark comparison. There are different benchmark, and we can see how Audio Flamingo 2 is working on that. Literally when we release it, it was doing a much better job than all the state-of-the-art methods around that time. And let me show some benchmark. These are the different benchmark, including our own MMAU. So state of the art was about 60. You can see we have huge improvement, like MMAU, our own benchmark, 61 to 65%, 56, 77%. So Audio Flamingo 2 was a big improvement. It's been very widely downloaded and used, and I strongly encourage you to go and play with it and try it out yourself. So let me show you some results, and some of the benchmarks are from MMAU. There was a question 10 minutes ago, and what kind of reasoning we do. Hopefully these benchmarks will answer some of the question. So this is so I play a long audio, and then I do my question answering, right? So the question is, what is unusual about this audio? And the ground truth was this audio really combined music and hammer beating, which is unusual. You don't see music and hammer beating. So this was like a really crafted audio, which is not a very typical benchmark. And if you ask all the previous benchmark, when we released it, at that time, the state of the art was Gemini 1.4, 1.5. And this was the answers they got, right? Literally, they did a good job. Whereas literally, Audio Flamingo 2 you could see getting close to ground truth. It's an unusual aspect audio and music and sound of mechanism. So you see, these are not your typical sounds like you daily hear. How time when you hear a music and hammer beating, which is unusual. So the goal was to really do complex reasoning. Here's an example.
A regular question coming up is, what's the cheapest smart trainer that I can get to use Zwift on? Well, I've answered that in my blog post about the Elite Cubo Digital Smart Plus. Hang on,
So this is a long audio, and again, I'm not going to play the whole thing in interest of time. It's a 5-minute audio. There's human speaking, there's music. So this is a very long sequence. I hope you can
and
go
the
play with
Bluetooth
it.
for me is not working. I'm sure it will work in other units.
So this was basically a long human speaking, singing sound of a different sound. So you play long audio and ask a question. When is a song with a male vocalist heard? Of course, I did not play the whole thing to you, so you could not see it, but the actual answer was in the middle. So this is like another reasoning question. Yeah, make you hear a long audio sequence, and where did you hear the male vocalist? There could be male vocalist, female vocalist, and ask this kind of question. This again is a benchmark from MMAU. So hopefully this answers the question that came up. And again, you can see different benchmarks did not do a good job, but at least Audio Flamingo 2, compared to Quen, our own previous work, Gamma, Gemini, did not do a great job. So that was it. And actually, just a couple of months ago, if you're playing with it, we released another version of, like, you can call it Audio Flamingo 2.1 or whatever this version 2.20250625 has just recently come out. So this further improved just MMAU on MMU sound, our own benchmark, CMM hallucination, mutual music, and cloth. So again, we keep on improving. That was the thing, because this model is already out. And of course, we keep improving how things get better. So that brings to the last part of my talk, which is our really latest project I'm most excited about and is forthcoming. So Audio Flamingo, this is just a term. This is 2024. And as I say, Audio Flamingo 2 has been out, although we present ICML next month. And you can see, what kind of tasks they were doing. There are a lot of slides here on the thing. We did Audio Flamingo 2 was coming up there. But our latest work, which is going to be releasing very soon, but you can see the demos and the paper is going to be out, Audio Flamingo 3, which is in a review. So Audio Flamingo 3 that we have done up, again, you can see we are advancing there. So one is that we're literally making a general purpose audio, and that includes speech, long speech understanding, thinking, and also we're doing what is called multi-turn, multi-audio chat. So I'll show you examples of that. It's very hard to explain this in words, what it means. So we're doing speech, sound, and music. And it's the very first model which can do long speech understanding and reasoning. And it can do multi-turn and multi-audio. So these are very unique capabilities that we're pushing towards it. And you can see how it's coming up. So before I give examples to you, of course, we get all kinds of data sets, right? There were existing data sets. Now look at the number here, right? So when it comes to speech, of course, there's 6 million question answer pairs and sound. But when we go to music, the data sets like 16, it goes quite bad. But then our own data sets, we call audio skills and long audio, which we introduced in Contact Group. And we have done some more thing here in the context called AF Think and AF Chat. So these are previous data sets. This is our previous work, our latest work as part of AF3. We have done quite well. So what is exactly the capability of AF3? So if you give me a long audio with instruction, right? So this is exactly the answering question you asked me about 20 minutes ago. You play long audio for 30 seconds, instruction, and describe the audio. And you say, okay, a man speaking with a long bang. I'll show more example like that, but you'll see this. So this is one of the audio skill was the first attempt on large scale audio question answering data set. Again, you can see a lot of details. Please check it out on this paper comes out. But also I want to give you that we also try to push for music. Now, music is, much more challenging and subtle because knowledge intensive domain where you can do it, but not everybody can understand good music. Like I'm personally have very poor music skills. And literally, how do you interpret good music? So we also trying to work with people and generating good music to do understanding there. So you have some long audio up to 10 minutes. It's the first one which can do 10 minutes audio, which I think is a big advancement audio language model and answer questions, So this could be very good for summarization, eventually audio to audio. So I'm going to show you a whole bunch of benchmarks, and hopefully that'll give you a sense of what we can really do in these models, and you can go from there. So let me show 4 or 5 different benchmarks, and literally, that'll give you all the challenging components and they'll come up there. But last thing I want to mention is the first system which can do multi-audio and multi-chat turn input. So imagine, describe the audio in a sentence and then audio bang, you add it. So you have 1 input, 2 inputs, and I'll show an example which demonstrates capability. And again, we book on Whisper, which is well known. Training was a big part, so we had to augment Whisper. We call AF Whisper training, which again was a big component in improvements we come up here. So this is the overall architecture. This is a training part, complex based on our AF Whisper, and this is a large language model. So this actually took us, it's a very complex model. And we had to get you access to about 1,500 A100 GPUs for 3 weeks. So this was a lot of resource, a lot of compute, and with a lot of big data coming out there. And here is you can see with every model, this stage of pre-training, encoder tuning, full fine-tuning, context training, chat and voice thing, the process just gets bigger and bigger. So this is one challenge we are doing is, as we make more models, I don't like our architectures getting more complex and more compute. As an academic, I wish there was a simple way, but that's a good topic for future work. But you can see this is a very complex training stages of AF3 here. You're showing results. We compare with lots of benchmarks, speech recognition. It's really coming up with sort of outperforming them for a lot of speech understanding. Expert reasoning benchmark, including our own MMAU, MMAR come up. We're showing pretty state-of-the-art numbers, and also with long audio, long speech. And in all aspects, we're showing that AF3 is either as good as state-of-the-art or even slightly better. So let me now next spend 5 minutes and towards the end of my talk and show you exactly the demonstration. Hopefully, a lot of questions that you're asking, semantic understanding, question answering, what we can do. So here I'm going to play an audio here. So this was, to be honest, a very out of tune saxophone in case your hearing audio is bad, right? And now I ask a question, what makes this saxophone performance unlike typical saxophone sound? It was probably, hopefully you can understand it was saxophone, but it was not a nicely tuned saxophone. So what makes it? So this is a question now we ask Audio Flamingo 3. And, literally Audio Flamingo gave some reasoning, and you can question that answer. The saxophones are played in a way that resemble the dog howling, creating a unique and unusual sound. So it was not a nice sounding saxophone. And we're asking you to reason, and the reasoning it came up is like, okay, it's not good, but it used the phrase resemble the dog howling, So this is, again, this is the kind of thing we're doing. Let me play another one. This is for, what I call different example of capabilities. So let me play other audio.
Oh, I must be in the wrong class.
Oh, no, you're in the right place.
Did I get the time wrong?
No, it's just you and me.
So you hear this two people talking, like a student, I'm in the wrong class, if you heard it right. And I prompt a question. Question number 1, right? How many students are in this class based on reasoning? So of course you could probably hear, right? What the answer A3, B2, C5, or D actually was 1. So actually, basically in this case, speaker mentioned just you and me indicating a small class size. The sound effects comes up here. So this probably the plausible answer is D1. Somebody could have said, oh, there were probably 2 sounds. Actually, if this was the D, only 1 sound, the answer was 1. But you can see this gets very subtle, right? How many different student voices did you hear? So this is hopefully give you example of complex reasoning, depending on how you hear. Sometimes human struggles, but this is the kind of capabilities we are trying to do this example with audio reasoning models here. Let's play other examples of captions here. So this is a classic song I used to hear when I was young, and literally I'm asking this question, generate a caption. So the question is generate a caption, describe the auditory scene in the input audio, considering spoken content, background sound, and music. So literally you hear, and I'm asking you to give the answer, and here's what Audio Flamingo does, probably a man is driving and singing a sad song to this thing. And I also really, literally say, if you do AR sound transcription, all it says is nothing really matters. That's the only part they could hear, like speech to text, And audio caption was the sound of a car and music in the background. So this is where things are going. Now let's get more fun. I want to deal with multiple audios. So let's see how it hears.
Tô cansado, cuspo fogo pra te esquecer.
In this case, I'm asking a question. Okay, this track feels peaceful, introspective. Now you can see, now this is a kind of a semantic understanding question. I know some people are asking me on the chat what semantic understanding means. So the track feels really peaceful, introspective. What elements make it feeling calm and meditative? So this is now, you see, this is not a little bit gets more complex question, right? It's a very semantic understanding. And let's see what Audio Flamingo 3 does. So we're reasoning that basically it came from, several factors. There was a gentle acoustic instrumentation, slow and steady tempo, soft expressive vocal delivery, arrangement leaves plenty of space, minimum percussion. So this is like, of course, I don't claim to be a music expert, but they're literally the choice of instrument, the tone, the tempo, the person who designed the music literally gave this. So this is the kind of reasoning we are doing. Again, some semantic understanding of what makes this music peaceful, introspective. So this is where things are literally coming in. You can see the multiple audio because there's an instrument playing, there's a human singing. So the multiple sounds come together and we analyzing. This is the kind of semantic understanding we are trying to do here. Now here's an example of what I call, multiple sounds here. So this was, the first song I played here. Now I bring what I call multiple audio sequences here, right? So this is what the part I'm doing. The users can chat multiple audio, but now I add a second audio input here.
It's hard to know what's coming.
Very different kind of music than the previous one. And now I ask a question here. Switching gears, if I want to remix the calming folk piece to the top left with something closer to what would you suggest? So imagine, don't ask much other question. I'm not the best music guy, but I want to remix them. And I ask Audio Flamingo 3, hey, what do you think if I try to remix chat with the multiple audio inputs? And it says, to transform the folk track into more energetic track is giving you suggestions. Start bringing the tempo, introduce electronic drum with a punchy danceable glove, replace the thing. So this is like, think of a musical advice. Now, whether it's good advice or not, I'll let you decide. I'm not a music expert, but you can see what it's trying to do. It's trying to analyze the two music understanding and giving suggestions how you can remix them. And this could be a very subjective answer, but at least you can see what Kbit is doing. Now, besides normally people do voice to speech or whatever, we also try and do voice to voice interaction. So this is an example of here.
What are the names of some famous actors that started their careers on Broadway?
And this output comes here.
Some famous actors who started their careers on Broadway include Meryl Streep, Whoopi Goldberg, Al Pacino, and Denzel Washington.
So
these talented individuals gained significant recognition and experience on the stage before achieving success in film and television.
So of course, it's again question answering, but except in the previous case, we were doing like literally, text prompt. So that's a question when somebody asked me, I said, the prompt itself could be voice. Okay, what do you do it? So that's it could be just voice to voice. And this is a huge implication. Just imagine natural conversation, someday doing language translations. So this is where this audio language model is heading. In a few years, we will do directly voice to voice. And this could be happening very soon there. So this is some demos. Here's a website. Please, all the demos, you can hear them long, calmly, and analyze them. So this is at least on GitHub right now. Please play with them. And hopefully that'll give you where things stand. So where are we today, right? So this is, I still say, as I conclude, sorry, I'm getting close to beyond 9 o'clock, 12 o'clock my time, that we are still in the very early days of audio understanding. I'm showing you some of the work we've done last 2-3 years, but we really have a long way to go. There are more questions, there are more challenges here than do it. Right now, most of your audio understanding, I want to audio generation. Can we make music? There's some example text music coming up, but it's complex music. And ultimately, we're doing mostly understanding. There are other people doing Meta, Google, so on who have generation. Can we combine generation audio? Like, generation audio show couple hand in hand, and nobody does a really good job at that come up there. How do you build models which can both understand input audio and generate one? This is again, we don't have good models there. The other part is all about reasoning and thinking. Now, this gets more really, that's what make LLMs, more challenging, at least on the language side, we have a lot of front, but especially the raw trend towards inference time computing, scaling, right? And can literally, scaling can compute audio generation by moving through the thinking paradigm. I think there's a lot of potential to do more work there. Clearly, we want to do more efficient. As I said, I was not happy that Audio Flamingo 3 is taking a lot of training costs and complex reasoning, right? The complex is a very subjective word. And I'm sure you can give me even more complex benchmarks, or you can even say, some of the answers I gave Audio Flamingo 3 were not the best answers. Humans could do better. I'm not going to disagree with you. That definitely comes up here. And last is, music. Music is much more subtle. How to be a good musician, that's the whole thing. So there are fundamental questions. But the very last slide I want to show you, I'm very excited about to benchmark. The two physical devices, the smart glasses, I myself use Ray-Ban, and now they have a very good microphone. They have 5 microphones and a speakers, left and right. Imagine the audio is much cheaper than video. can you imagine here the audio outside and you do audio understanding, you filter it. So integrating this into your smart glasses, AirPods there. I also do a lot of work in robotics, and there's a lot of interest in robots, humanoids, all doing vision, cameras, LiDARs. When will the robots have ears? I don't see many people working on, they're trying to bring robot amazing computer vision, scene understanding, and vision is the most important cue. What about hearing? So I want robots to have the same complex understanding and reasoning of physical AI. I think that's the world we're getting towards when our this audio capability is integrated with smart glasses, IoT devices, robots. We'll have a different world. So I'm sorry I went over time. Thank you all my sponsors and collaborators, and I'll take more questions. I don't think I answered all the questions in the chat, but if it's okay, I can take more questions now. Please go ahead.
Sure. I don't know why there's a echo. I don't know. Could you hear me well, or there's echo?
Yeah, I can hear you.
Okay, perfect. So thanks a lot. It is like a very comprehensive presentation. So there are a couple of questions in the chat, and I also have one question that I want to ask. So I have seen in lots of reasoning tasks that when you provide transcription of the task, the reasoning improve. Or in general, it seems that when in the text, the reasoning is better. So I want to have your opinion about the difference or the difference that between the text modality and speech modality in the reasoning domain.
Yes, that's a really. I think I'm hearing echo. Are you hearing my echo too?
Yeah, maybe you could stop sharing and reshare without the sound or something. I don't know.
Okay, is it better? No, echo
No,
still
no,
is
we
there.
are still it.
Okay, so I think. Maybe. Okay, is it better now?
Yeah.
Okay, thank you. So, the speech, the text part is, as I said, in some way for a lot of people working in audio, we got this wider audio language model. We say, okay, it's Chat GPT, text was a big one, right? NLP field has changed forever. And they're getting better and better. So clearly, the kind of answering Chat GPT gives us, Gemini gives us, reasoning is really, really good, right? Now, you're absolutely correct. We were playing the sounds and giving audio captioning question. The text part, the technology is getting much, much better. But the audio reasoning, audio understanding part is still much weaker. And there are reasons for that, because as I told you, the biggest challenge I see is that amount of data we have for training. So a lot of our focus has been on non-speech audio, complex audio. And we're talking about billions of tokens in speech or text, and we're talking about a few tens of thousands of tokens. So one of the reason our capability is not so good because we don't have so much complex audio samples available with the ground truth labeling of audio understanding. And that's for the reason I talk a lot about synthetic data generate that. So the lack of data is a very big challenge. So, to really make improvement, we will need a lot more data. That's always the case. So that's why there's a gap between the speech part and the actual audio part. And you have that my benchmark.
I see. And maybe one additional question. In your benchmarking, have you observed any difference when you encode the audio with discrete tokenizer or with like something like Whisper? And which one do you think it is better for the reasoning task?
Yeah, so that's again excellent question. We actually tried both. Like of course in the latest one, the Audio Flamingo 3, we took Whisper and we extended to what we call AF Whisper. It's an extension of Whisper. So right now, I think we're getting better. I will not say the one is universally better. We played with both of them. But right now, in the latest one, the fact we didn't call it AF Whisper, build on Whisper, we're seeing better results with that right now. But but these are heavy topics. Tomorrow, will not be surprised somebody publish a nice paper, hey, I did discretized distortions. But right now, we're observing good behavior with the best behavior with our AF Whisper as of today.
I see.
But these are hot topics of research. They change every few months.
Sure. So maybe there are a couple of questions in the chat. So one question is that how far do you think we are away using this improved model for reasoning for using as an audio evaluation task instead of the metric that people use like MOS, SNR or something? Right. Do you think that they could be used as an evaluation metric?
Absolutely. So those, those are classical, what I call, those metrics are classical signal processing metrics, right? Signal to noise ratio and this thing like there. But you remember a lot of audio, especially, remember I give you an example of music, right? Music, no, I'm not a music expert. I don't pretend to be one, The music understanding is very subtle. right? What if you ask some professional musician, what distinguish a simple amateur versus a professional musician? So I'm hoping that actually now that we can eventually do some better generation, we can train those metrics. Eventually, we can do much better understanding. So we're still in the early days of audio understanding, especially with complex music and audio. As this gets better, I will not be surprised, more and more people start using the system for better understanding. But of course, we have to do the same metrics. Eventually, we need, I think we should get some really professional, even like when you people do audio, right? They do really good hearing tests, right? They will, like especially studios do that. You have to put a nice headphone. There has to be no reverberation, very good setup. So those tests and those evaluation, even if you go to, audiologists, those are very expensive, right? So, but of course, then we would need a lot of good labeling data with those ground truths. So that'll be the challenge there.
That's it. Okay, there's one question about the long audio problem that you mentioned. Is it like, could we just split the audio into a smaller segment and using a sliding window and ask the encoder, and that in that way it could solve the problem, or there's some issue regarding that?
So that's in fact, that's a very natural thing. In fact, even if you look at Audio Flamingo 3, right? I very quickly show the architecture here. Let me sorry. That's a natural thing. The challenge comes out to be, you're right. Let's say if I show a 10-minute audio, right? Could I break up into 10 1-minute sequences, right? But then a lot of questions are, remember the question I'm answering, where the things sample. So something are more continuous. How do you split? So if you know semantic understanding the audio, then you could, it's like imagine you're watching a movie, right? And movie, like average capture scene is about 5-10 seconds, right? So you do it, but they're uneven, right? So if you're seeing an indoor scene, outdoor scene, you can split. So if you have a semantic understanding of the audio, where you know the audio context and tones change, do it, but that becomes chicken egg problem. Here, what we're trying to do is like, I give you the long sequence and how you do with it, that's what we're doing here. So yes, that's what you're saying is a very, will make my problem much simpler. But if my split is just on discrete pre-chosen 1 minute each, right? I may lose some context, and there could be a part. So then how do you do the temporal continuation between them? That becomes a problem.
I see. I see. There is one general question in the chat. It is like the research project are very interesting and looks like lots of effort will put into them. How long does it usually take to complete such project?
Oh, I have a lot of, you look at our papers. So we have a good group of, I have 7-8 students at UMD, but we also work with NVIDIA, especially AF3. So, as I'm sure any of these, any language model, if you've done a new language model training, and as we do more and more, AF2, AF3, right? More training, more he's there. So that clearly becomes an issue. Yeah, and then believe it or not, I joke, I teach in my classes. The two big important for any of these projects has been any big large language model. You need a lot of compute. In this case, we work with NVIDIA. We got GPUs from them. I don't have so many GPUs at UMD, but 80% of the job I say about data curation, because literally we don't have data.
Yeah.
That's in audio, non-speech audio, we just don't have data. And I wish I could, crawl the internet. So I joke, and then of course you need a lot of compute training and everything comes up there. So yes, data curation is always a challenge. And I keep on saying, every third minute I was saying data. So I wish, I wish of a larger community efforts that we as a larger group of people work on data. That's what it takes.
I see. And maybe I have one final question. I'm just curious. Like, I have seen many reasoning tasks as the audio input and the text output, and then I have seen that you show the result with audio to audio. Right. How challenging it is, and what is the performance when you have audio to audio reasoning? But just so curious about that.
Yeah. So you see, there was some question I think on chat too. There's a lot of work on text to speech and speech to text. So speech audio. In fact, I was looking at Gemini 2.5 have a very long tokenizer. They can do even long, audio to speech. So clearly, speech audio to text and TTS and that's a pretty well studied. So that's definitely you're done. Now audio to audio, so that's the well part. Audio to audio is still very new, and that's what we ultimately want, because we want audio to audio because. Certainly, one of the application I want to do is like think of real-time translation. Let's say you speak in your language, whatever. You're in Canada, you're bilingual, right? And I'm new to everyone. imagine I want to real-time translation. And human, if I'm talking to you, our audio cues and visual cues has to be in sync. If your audio is delayed, let's say by even 30 milliseconds or like 500 milliseconds, so I can take your speech, convert that to text, of course, and text to text conversion and text to speech. But going to text, converging in text, intermediate makes it harder. So that to latency, and that becomes very irritating to humans, like even audio visual there. So I would think, especially video to voice to voice or audio to audio, has a huge implication of low latency. There are a lot of applications on low latency, but what's harder? Well, we don't have so much, the amount of work we had on speech to text or text to speech is significantly much better. That's what happens there.
I see. Perfect.
So again, we would need a lot of data. Just imagine, and imagine someday you're asking me a question, let's say, whatever, let's say, I know Canada is bilingual. I don't know, we're like in Montreal, I love being this thing. Imagine you ask me automating French and I'm automating real-time low latency translation in English, and I'm answering. Imagine someday we're having conversation like this. That's one of my dreams. And I come from India, which is a country of God knows 22 official languages and 300 unofficial languages. Just imagine a language diversity we have, how nice would it be that we can converse with each other with low latency voice to voice? That's my dream. And because data we would need to be a long way to go.
Yeah, I think the QTI, the company that generate Mimi, also released something called HipKey or something that they kind of try to handle this translation thing. But yeah, I agree. There's a long way to achieve a very good.
But I'm saying the very fact you want to voice to voice because you want natural chat, and I don't want to go to text and convert use text intermediate form. I know there's a lot of language. I see Google Translate, all the translate really good for language. Language is easier, audio is harder, and partially because we don't have much data experience. So this is a whole new research area.
Yeah, I agree. Perfect. Thanks a lot. I think that's a very informative presentation. Thank you for joining our presentation, and thank you for the talk. Thank you, everyone. We won't have a meeting for 2 months, but we will be back in September, and I hope to seeing all of you then.
Thanks for organizing. If anybody has questions, feel free to email me or look at our website. Thank you for giving me the invitation.